Understanding the rates of reaction is crucial in the field of chemistry, as it sheds light on how quickly reactants transform into products. When we talk about reaction rates, we're referring to the speed at which a chemical reaction occurs. This can vary significantly from one reaction to another. Some reactions are instantaneous, like the explosion of fireworks, while others can take hours, days, or even longer, like the rusting of iron. To grasp the concept of reaction rates, we must delve into the factors that influence them and the underlying principles governing these processes. At its core, a chemical reaction involves the interaction of particles. These particles are atoms and molecules that must collide with one another to initiate a reaction. However, not just any collision will suffice. These particles need to collide with sufficient energy, a concept known as the activation energy. This is the minimum energy required for a reaction to occur. Think of it as a barrier that the particles must overcome to transform from reactants to products. If the energy of the colliding particles is below this threshold, they will simply bounce off one another without any reaction taking place. The rate of reaction can be influenced by several factors, including concentration, temperature, surface area, and the presence of catalysts. Let's break these down. First, consider concentration. When the concentration of reactants increases, there are more particles in a given volume, which leads to a higher frequency of collisions. More collisions mean a greater likelihood of particles colliding with enough energy to react, thus increasing the rate of reaction. Next, temperature plays a pivotal role. As the temperature rises, the kinetic energy of the particles also increases. This means that they move faster and collide more frequently. Not only do they collide more often, but the energy of these collisions is also greater. This increase in energy raises the chances that the collisions will have enough force to overcome the activation energy barrier, resulting in a quicker reaction. Surface area is another key factor. When a solid reactant is involved, breaking it into smaller pieces increases its surface area. This means that more particles are available to collide with other reactants, thereby enhancing the rate of reaction. For example, powdered substances react more quickly than larger chunks because the powder exposes more particles to potential collisions. Catalysts also deserve special mention. A catalyst is a substance that speeds up a reaction without being consumed in the process. It works by providing an alternative pathway for the reaction with a lower activation energy. This means that even at lower temperatures, particles can collide with enough energy to react, thus accelerating the overall rate of the reaction. To visualize these concepts, we often turn to graphs that depict reaction rates. A common representation is a concentration versus time graph, where the rate of reaction can be inferred from the slope of the curve. A steep slope indicates a fast reaction, while a gentle slope suggests a slower reaction. Understanding these graphs is essential for interpreting data and drawing conclusions about the nature of the reactions being studied. In summary, the rates of reaction are influenced by several factors that determine how quickly reactants can turn into products. The necessity for particles to collide with sufficient energy underscores the importance of activation energy in chemical reactions. By manipulating concentration, temperature, surface area, and catalysts, we can control the rates of reactions, allowing us to optimize processes in everything from industrial manufacturing to biological systems. Mastering these concepts not only deepens our understanding of chemistry, but also equips us with the tools to harness these reactions for practical applications in our daily lives. The interplay of these factors is a fascinating dance of particles, energy, and time, revealing the dynamic nature of the chemical world around us.